Example 7.1. A. Describe the behavior of the capacitor's voltage, initial and final steady states, charging or discharging. And then B. Determine the capacitor's voltage for t greater than 0. Plot the voltage versus time from minus infinity to positive infinity. So let's look at this thing first. So we want to ask the question, what is the physical behavior of the capacitor? So when I look at this thing initially, I have t equal to 0 minus. And when you look at the circuit, note that the switch closes at t equal to 0. So in the beginning, there is no 6 ohm resistor. So what I'm really seeing here is that I'm seeing something like this. I have a source that's 3 volts. There is no 6 ohm resistor. And then the capacitor goes to a steady state. So in other words, this voltage VC of 0 minus, you could see here is that the voltage of the capacitor sees the full voltage. So you could see here is that the cap sees the full voltage of the battery. Now, what ends up happening here is that once the switch is thrown and I let this thing go to steady state, so there is a 6 ohm resistor now. So now if I draw the circuit, you could see that I have 3 volts, and then I now have these resistors right here. And so what you're seeing here is that now this is VC of infinity, which is really VOC. What you're seeing here is that now the cap sees only part of the voltage source, that is. He only sees part of the voltage source. So what this tells us here is that from this picture, we see that VC of 0 minus is greater than VOC. So therefore, we see that the capacitor discharges. So that's really important to understand, because if the capacitor, you get an answer that shows that the capacitor is, charging up, it's got to be wrong. Okay, so here we go. So now what I'm going to do here is that I'm going to follow the 4-step process outlined in lecture. Okay, so here we go. So what I'm seeing here is that I'm going to go to my first step. So my first one, I'm going to go step 1. And what the goal here is that we want to determine VC of 0 minus, but we're really after VC of 0 plus, and we know that the capacitor cannot discharge instantaneously. So here we go. So at t equal to 0 minus, the switch is open. And all resistors are dead. In other words, there's no current flowing. So we already saw that initially, but now I'm just going to do it like this here. So with the switch open, there is no 6 ohm. So here I have a 3 ohm, here I have a 6 ohm, and then this guy right here is VC of 0 minus. So immediately, because these guys are dead resistors, you could see that the voltage of the cap has to be the same as the voltage of the source. So I have VC of 0 minus, but I'm only interested in 0 plus, and we know that is 3 volts right there. So now I have the initial voltage. Now I'm going to go to step 2, and I'm going to determine the Thevenin parameters at t equal to 0 plus. So what that really means here is that I only need 2 things, but I really need what? I need VOC, I need RTH, but I'm only using RTH to get 1 over the time constant. And this is after the switch is closed. So now I have a Thevenin circuit. So that means I got to do what? I have to remove the load. Okay. So if I remove the load, so in this case, I'm going to remove the load capacitor. And here's my circuit. So what I have here is that I now have a 3-volt source with a series of resistors that look like this. So this is my A, B, and this is 3 ohm, 6 ohm, 6 ohm. So now you see that I've got to go in and do that. So here we go. So my first step that I got to do here is that I need to determine VOC. So if I look at VOC, my circuit tells me this. I see here that I have a 3-volt source and this guy here gives me plus minus VOC. Again, this is a 3 ohm, a 6 ohm, a 6 ohm, and you could see that because of the open, this is a dead resistor due to open. No current flows through it, so therefore there's no voltage drop. So now what I see here is that the voltage VOC is the same as the voltage of the 6 ohm resistor. So because this is a series circuit, use VDR. So when I look at that, I see here is that VOC is the same as the voltage across the 6 ohm. Now using that, I could see here that that's going to be 3 plus 6, all into 6 times 3 volts. So I see here is that this is going to be 2 volts. So now I have my Thevenin voltage right here. Now, at this point, this is an important check. So here is an important check. Initially, we determined the capacitor discharged. Now we have the ability, right? We said that VC of 0 minus was going to be greater than VOC. So let's check that. So when I look at VOC, you can see that that's 3 volts. So now I'm comparing VC of 0 minus, which is 3 volts. This is greater than VOC, which is equal to 2 volts. So that checks out. So this is a good thing. Okay, so at least we know we're moving in the right direction. So now I'm going to do the next thing where I want to go determine R Thevenin and 1 over tau. So there's no dependent sources. So I will use method 1. I could use method 2. That totally works. So what I'm going to do here is that I'm going to short out the voltage source. So the 3-volt source is gone. So if it's gone here, so then I'm going to have this resistor right here. Here's my 3. Here's my 6. Here's my 6. And then here's the open right here. And then I've shorted out the voltage source. So here's 3, 6, 6. And I am looking right in here as my Thevenin voltage source. So using Thevenin resistance. So now I'm going to use resistor reduction to get this. And resistor reduction says that RTH, I'm going to have 6, and then 3 and 6 are in parallel. So 3 and 6 gives me 2. So therefore, this is 8 ohms, which is now RTH. So now I have RTH. So from this, I now am going to the time constant is tau, which is then R Thevenin times the capacitance. And you could see here is that I now have 8 ohms. The capacitance is 0.05 farads, and that gives me 0.4 seconds. Now note, we're not really interested in the time constant. What we're really interested is 1 over the time constant. So if I do that, I get 0.4, and then this gives me 2.5 hertz, or 1 over tau. So now I have all of my Thevenin parameters that I need. So let's go put this together now. This is step 3. So now what I'm going to do here is that I'm going to put this into solution form. And interpret. So the solution form says that VC of t is then going to be VOC plus VC of 0 minus VOC times e to the minus t over tau. So if I start to put in my values, you see this is going to be 2, 3 minus 2, and I'm going to get e to the minus 2.5 t. So if I clean this up, I now find that this is going to be 2 plus e to the minus 2.5 t. So now I can summarize everything. So in summary, even though I don't have to do this, I'm going to write this out anyways. That solution is enough that I just wrote here. But to make it a little bit cleaner, note that this is going to be 2 plus e to the minus 2.5 t. And then this is going to be 3 volts here. So this will be t less than 0, and this will be t greater than 0. So that is my solution. Once again, I could have written just the bottom solution because it's also correct for that other one. So now what I want to do here is that I want to go in and interpret the solution. Okay, so now my job here is to interpret and plot the solution. So the first thing that we should do here is that, look what the solution shows. So the solution has VC of t, then I'm getting a 2 plus 1 times e to the minus 2.5t. So remember a couple of things here. That plus here tells me that it discharges. If I have a minus sign, it charges up. And then the second quantity right here tells me how much it discharges. So to show you what I mean by that, let's plot this. So if I look at 2, so now we're going to plot VC of t versus t. So what you're seeing here is that you're seeing this. So we know, so if I look at my curve, it looks something like this. So what I'm seeing here is that I know that this guy is coming in, and this is VC of 0 minus is 3 volts. And then I can see right here that this guy is going to discharge to VOC, which is equal to 2 volts. So then I'm going to see a curve that goes down like this here. And so this curve is described by 2 plus e to the minus 2.5t. Now, look at the discharge voltage. So if I look at this guy right here, you could see that the drop from here to here has a voltage drop of 1 volt. And look at that 1 right there. So this is exactly what we'd be seeing here. Now, another thing that we should really look at here is that even though the voltage is continuous at the boundary, in other words, VC of 0 minus must equal VC of 0 plus, the capacitive current is usually not continuous or piecewise continuous. In fact, we should see a discontinuity. So remember, from minus infinity to t, that told us that the capacitor was an open, which that immediately tells us that this guy is 0. However, at t equal to 0 plus, the current of the capacitor, in this case, is the derivative of the voltage. So let's look at that. So this is going to be at 0 plus, so I got to take the derivative of this. So here I go. I know the value of the capacitance. Then I'm going to take the derivative of 2 plus e to the minus 2.5 t. And then I'm going to set t equal to 0. And so when you compute that, you're going to get a value that reads something like this. I'm going to get 0.05. I take the derivative of the 2, that's 0. I take the derivative of the exponential, so I'm going to get minus 2.5, then e to the 0. And so this gives me minus 125 milliamps. So compare them. So if I now compare, I see that IC of 0 minus is 0, versus IC of 0 plus is equal to minus 125 milliamps, you can clearly see that there's a discontinuity. So if I now graph this thing, so if this is my graph right here, here's what I'm seeing. So this right here is going to be IC of t. And so what's going to happen here is that, here I come. When the capacitor is in open, I can then see here is that this is going to be equal to 0. So now what happens? At 0 plus, this guy jumps all the way down to this point here, and this is IC of 0 plus, which is minus 125 milliamps. So you could see that from here to here, it's discontinuous. There's no continuity. It's discontinuous. There's a discontinuity. At t equal to 0, as we would expect.